In this video, we're going to discuss phase changes. So, energy, so we talked about the calorie. 1 calorie was the energy for 1 gram of water to go up 1 degree Celsius. This means that energy is tied to the temperature changes of material. And if you think about what we use heat for, you burn log, burn methane, run a stove with electricity, anything like that, we generally heat up food. Like you get your water to boil to cook pasta or rice or anything else. Heat causes temperature change. There is an amount of energy necessary to make those changes. So let's talk about how we go from, say, a solid, heat it up to let it melt and become a liquid, or heat a liquid up until it boils to become a gas. If you were to start with a graph that had minus 20 degrees Celsius, so we have a temp side, and we have an energy side. What will happen, let's use water. I have an ice cube. Well, ice is around when water is below 0 degrees Celsius. So what's going to happen is I add energy. So I go higher in energy. We are going to see that the temperature of our ice goes up. Normally we think of ice when it freezes, but you can get it colder. Like if it's out in the mountains and it's way below 0, that ice is well below 0. So it's going to warm up the ice cube, but it's still ice until it hits the melting point, 0 degrees Celsius. Once you hit 0 degrees Celsius, it's no longer ice, right? So it started ice, it hit 0. But curiously enough, while you are taking your 0 degree ice cube and you start putting in energy, it doesn't get hotter. While we are melting or freezing, you don't go up or down in temperature. Can imagine, basically you got an ice cube. And so here's my ice cube. And if any water should form and start, dripping down and pool, well, it's in contact with the ice cube. So your ice was at 0, you put in a little energy, and some of it broke free and turned into liquid water. But that liquid water is still touching the ice cube, so it's still at 0 degrees. It just keeps the same temperature. The energy is actually going in to break the solids apart. Your solids have a nice ordered structure. You need to put in energy so that a few of these can break free and start rolling around to look like a liquid. Remember, liquids are more free-flowing. They're spaced out a little bit. They're not quite in a nice order. They flow between and around. The energy you are putting in while you are melting is actually to pop the atoms, or the molecules in this case, out of the solid and get them free moving. But temperature, what you tend to feel as temperature, is a average of the kinetic energy, the vibrations and the shaking. Even though they're up freely moving around, they're not shaking any harder. They're not transferring any more energy into the things that would measure the temperature. The net result is that while you go through a phase change, as you go from solid to liquid or reverse, or from liquid to gas or reverse, you do not change your temperature. But eventually, all of that ice cube will melt away. You'll just have a pile of liquid. Now any extra energy you put in is going to heat up that liquid. And so eventually all of our ice melted. We started putting in more energy and it started to heat up, until eventually that water reaches the boiling point. At which point you go from being liquid to boiling away. But if you've ever had water on the stove, it doesn't instantly flash into gas. It boils for a while. So you have to get water up to the boiling point, and then you have to continue to heat it for it to boil away. If you've ever had a boiling pot on the stove and you turned off the heat, it's still very hot, but it stops boiling very quickly. As soon as the heating coil or the gasket turned off, it basically stops boiling. You actually have to put in more energy to convert the 100-degree liquid into 100-degree gas. So boiling or condensing, if you're going from gas to liquid, during those changes, you do not change your temperature. Eventually, all of your liquid has become gas, and any more energy will cause the temperature to go up. But it will be temperature of your gas. This is true for all materials, not just water. The temperatures at which they melt and boil will be different, but the idea is you have a material, you put energy into your solid, it will continue to heat until it reaches its melting point. You continue to add energy, and during that time, it will not get hotter. It will stay the same temp while it melts. Once it's all liquid, more energy will cause the liquid to warm up until it reaches the boiling point, where more energy will cause it to turn into a gas, but will not cause it to get hotter. Well, this gives us a couple different regions. There's a region where I can get hotter by putting in energy. There's a region where I can melt by putting in energy. There's a region I can get hotter as a liquid by putting in energy. There's a region where I can boil by putting in energy. And there's a reason where I can get hot as a gas by putting in energy. These all take different amounts of energies and different approaches to calculate. So let's talk about the two. There is a fairly simple formula for finding the differences. Q, which is a shorthand for heat energy, Q equals ms delta T, where m is the mass of your sample. S is a value called specific heat. We'll talk about it's a constant that is unique to every compound and every phase. And delta T, the change in temp. If you only want to heat water up a little bit, you don't have to leave it on the stove very long. But if you want to heat it all the way to boiling, you have to leave it on longer. The bigger your change in temperature, the more energy is going to be required. So let's talk about all of these by walking through a problem. Let's say I have 10 grams of liquid water, and I want to go from 25 degrees Celsius up to 85 degrees Celsius. We're going to do a reaction. We got some room temp water, but I need it hotter. So we're going to increase its temperature up to 85. How we would calculate it is that the total energy required, the Q, it's going to equal the mass. Well, for us, that's 10 grams of water. And so I can get the mass. And then S value. So what is S? S value, the specific heat for water, is actually what we saw for the calorie. It tells you how much energy for your material to go up in temperature. So for water, the S value is that it takes 1 calorie for 1 gram to go up 1 degree Celsius. The way we write this is that the S value for water liquid is 1 calorie per gram degree Celsius. What'll happen when we multiply is those grams will cancel out. The one from the weight is on top. The one from the S value will be on bottom when we multiply and divide. If you had 1 gram of water and you wanted it to go up 1 degree, it'd take 1 calorie. If you had 2 grams of water, they would each take 1 calorie, and you'd need 2 total calories. I have 10 grams of water. Each gram is going to take some amount of energy. And since we're not going up 1 degree, I've got a delta T. We're actually going up multiple degrees. How many? Well, your delta T is always equal to temp final minus temp initial. So for us, that's 85 minus 25. So it's going to be an increase of 60 degrees Celsius. So 10 grams, each gram needs to go up 60 degrees, and it takes 1 calorie for each gram to go up 1 degree. So 10 times 1 times 60, we're going to find that the Q here is 600 calories. To get this 10 grams of water to go up 60 degrees requires 600 calories of energy. So let's look at this again. So we've got 10 grams of water that went up 60 degrees, and it took 600 calories. But that was water that started here at about 25, and it went up to here about 80. I was within a phase. I was liquid at the start, and I was liquid at the end. That formula, Q equals ms delta T, is for in a phase. You have to start and end the same phase, solid, liquid, or gas. What happens if that doesn't happen? How do I deal with going through a phase change? Well, if I start with some ice and I melt it, I definitely put in energy, but there's no temperature change. My delta T is 0. And 10 grams times 1 times 0 doesn't matter, it's 0. You cannot use this formula, Q equals ms delta T, while going through a phase change. So there's a separate formula. Q equals m delta H for a phase change. Delta H is another constant. It's unique to every chemical and every phase change. For water, the delta H of fusion, which is the melting, freezing, for water, is equal to 79.7 calories per gram. So when we thought about a solid nicely arranged, and we wanted to break some of it free and let it start rolling around, to do that, we have to put in energy to get that moving. That is the energy of fusion. That requires 79.7 calories per gram of water to get them freely moving around. And so if we had 10 grams of water solid at 0 degrees Celsius, and we wanted to turn it into 10 grams of water liquid at 0 degrees Celsius, just to melt it, the equation would be Q equals m delta H. In our case, our mass again is 10 grams, and our delta H is 79.7 calories per gram. Each gram will take just shy of 80 calories. I have 10 of them. So in the end, 797 calories is required for this 10 grams of ice to melt. It actually took more energy for the ice to melt than it took to go up 60 degrees as liquid water. A phase change is very energetic. It takes a lot of energy for something to melt or to boil. And here's how we can calculate those differences. Now, what values will you need? S values for water. If you are a solid, it is 0.486 calories per gram degrees Celsius. S value for water, if you're a liquid, well, we said that was 1 calorie per gram degrees Celsius. That was the definition for the calorie. So that one's perfectly accurate. We're not generally heating up gaseous water, so we'll stick with these. The delta H of fusion for water, to go through melting or to freeze, is 79.7 calories per gram. And the delta H of vaporization, to boil or to condense for water, is 540 calories per gram. Significantly more. This is always the case. Your vaporization delta H will always be greater than your fusion delta H. Just getting things rolling they're still in contact with each other. So a fusion doesn't take nearly as much energy as a vaporization, which has to completely pull every molecule apart to turn them into a gas. Any work we do would be done with water, or you'll be given S values for other chemicals, but here are the common ones we will use for water.